Continuing our journey in chapter 12, we're going to get into the heart of why things happen, which is the reaction mechanism. And ultimately, why they happen or how they happen dictates how fast they happen. And so there's the learning outcomes expectations. Feel free to pause and read through those before we continue. So we talked about reaction rates, factors that affect them, rate laws, integrated rate laws, time concentration equations. We talked about collision theory, the three things that must happen for a reaction to occur, which is why there's temperature and concentration dependence. But ultimately, again, like we said, molecules have identities, and that dictates the reaction mechanism, how they actually transform from one thing to another. And so there's our list: collision rates. We have our reaction formula. We have a start. We have a finish. That's where we began and where we end after everything occurs. We talked about how fast it's going to happen. That's based on the Arrhenius equation, temperature and concentration, how temperature dictates rate constant and how concentration dictates the number of collisions. That's going to get you the rate of the reaction. But if we want to talk about the details of everything in between, not just how fast it happens, but why it happens the way it does, that's when we're talking about reaction mechanism. And so mechanism is basically what individual steps go into making, turning reactant A into product B. And so for that, we spend a lot of time talking about these reaction coordinate diagrams. And we introduced this previously, and so here's just showing an example. But instead of, just A nebulously turning into B, here we're going to make it a little more like these are actual molecules. So you take a molecule composed of A and B, a molecule composed of C and D, and ultimately if it's going to make A, C, and B, D, you're going to break an AB bond, you're going to break a CD bond, you're going to make an AC, you're going to make a BD. And so that's where this reaction coordinate diagram comes into play. And so on this diagram, we have reactants, we have products, and we have the driving force for the reaction. And so chapter 16, we'll get into thermodynamics, but it basically says starting point has reactants has this energy, products has this energy, there's a driving force. So the overall energy that's going to be released or put into the system is going to be dictated by this driving force, whether it's endo or exothermic. We also have an activation barrier. Remember back to our Arrhenius equation, the rate constant is dictated by the pre-exponential times z, and then you have activation barrier r and t. And so this activation barrier dictates how fast it can get over that hill. And so that's the EA, or activation barrier. When we're talking about mechanisms, we're going to introduce something new, which is known as the transition state. Basically, you have reactants that have a very particular identity, a particular connectivity, and you have products, the same thing, identity, connectivity. You can isolate these guys, you can characterize them by things like NMR and mass spec and things like that. But between reactants and products, something has to happen, right? Bonds are making, bonds are breaking, and you're going through up the hill, and you're going to reach something called a transition state. And basically, what is the molecular composition or atomic composition? How are atoms connected at the high energy point? And so here's the formal definition. It's a short-lived high energy configuration of atoms at the energy maxima in the reaction energy diagram. And so it's not reactants, it's not products, it kind of looks like something in between. Typically these are really hard to characterize and identify. And so there's some techniques you can do to figure out what, the structure of this is, but these can't be isolated. You can't jar this up and put it on a shelf, because no matter what, it's going to want to turn back into reactants or turn into products. But you have to go through this transition state. You have to, start breaking AB bonds and CD bonds and start forming AC. And so that's why this is squiggly lines. Like all your Lewis dot structures and things like that thrown out the window during this transition state, because it's not reactants, it's not products, it's something in between. And so one thing to note about this diagram is if there's one hill, there's one step. You're turning A to B, and it's only going through one transition state. But reactions can happen through multi-steps, and it depends on the nature of the materials. But here's just one example. We're going to take 2NO plus O2, giving us 2 NO2s. And so we're making an oxygen-nitrogen bond, breaking an oxygen-oxygen bond to give us this NO2 product. And so again, we have reactants and products. We have a driving force between the two. That stays exactly the same. The major difference between a single step and a multi-step is we have two hills to get over. We have hill 1 and we have hill 2, and that's what tells us there's two steps. And so we have step 1, it's going to transform into something. Step 2, it's going to transform into something else. And so for this particular reaction, step 1 is 2 NOs reacting to give you N2O2, and then N2O2 reacts with O2 to give you NO2. And so note, when you combine this together, you still get the overall reaction, but it's happening through a multi-step process. And so for each of these hills, we have a peak on that hill, and that's the transition state. Remember, transition state is this nebulous thing. It's not reactants, it's not products. It's something in between those. You have transition state 1, transition state 2. You can think of step 1 as reactants, products, and then step 2 is reactants and products. And so you can break it down into single steps. But for the overall reaction here, there's a 2-step process, 2 hills, 2 transition states. We have 2 activation barriers as well. And so for reactants to go to products in step 1, it has to get over this hill, this activation barrier 1. Now for the second step, you have the products from the first reaction. They're now the reactants going to products. There's another hill it has to get over. And so there's an activation energy for the first step, activation barrier for the second step. One important species to delineate here is something called an intermediate. And so here you can see the definition: a species that is produced in one step and consumed in the subsequent step. And so if you look at your reaction diagram here, you start with reactants is this, products is this. We have this N2O2 species that's not reactants or products, but it is generated and subsequently consumed. And so when you do the overall summation of this reaction, step 1 plus step 2, N2O2 cancels on this side, N2O2 cancels on this side. Overall, N2O2 does not show up in the reactants or the products, but it is generated during this process. And so when you go up over the hill, transition state down to a valley, you generate what we're referring to as an intermediate. This N2O2, it's in this dip. It is the product of the first step. It is a reactant in the second step. Again, it appears in the steps, but not in the overall reaction. And so something to note about this, sometimes these intermediates can be isolated. So unlike transition states, which are really nebulous and not stable, intermediates can have very specific identities. Sometimes you can jar them up and sell them. But when you do the overall reaction process, it's not a reactant, it's not a product, it is an intermediate during that process. So you go from reactants, transition state, intermediates, transition state, products. And so we talked about 1 step, we talked about 2 step. There's nothing stopping a reaction from being 30 steps. And so here's just a couple examples, cartoonish depictions of a 3-step reaction process, a 4-step reaction process. And so you can see, again, you have to get up the hill, reactant to product, first transition state, first step, reactant to product, second transition state, second step, reactant to product, third transition state, third step, so on and so forth. And each one of these steps has an activation barrier. There's 1, there's 2, there's 3. There's an overall energy, there's reactants and products. You can break it down into individual steps. The point is that these reactions can get very complex, right? They don't just all happen A to B in 1 step. Many things can occur in the process, and really understanding these is how you make reactions faster. And so let's take a 4-step reaction where we're going to turn A plus 2C into a G. And so you can go through and do your letter math. You can figure out what the intermediates in this case are. The answer is we have B, D, and E are in this reaction, but not in the products. You could draw 4 hills for this reaction. You could draw 4 transition states. You can put the intermediates in each single step, and multi-step reactions get very complex. And so what each of these steps is commonly referred to as an elementary step or an elementary reaction. And so it's a single step, reactions going to products, and then you sum those together and you get the overall process. Again, each one of these steps represents a hill on the reaction coordinate diagram. One thing to note about each of these steps is you can think about each of these as being an independent reaction, right? A going to B is something that can happen. Now, B might go through subsequent steps, but we can treat this as an individual step. And because it's an individual step, we can think about it as a single reaction, a single product reactant, a single rate law associated with that. And so one of the nomenclatures we use associated with these is molecularity. It's basically the number of molecules that come together in an elementary step. It says, how many molecules or how many species come together to do this reaction. And that's actually related to the rate law. And so for each single step, we have a rate law for each of those steps, right? There's an overall rate law for the entire reaction, which we'll get into later, but we can draw a rate law for every single step of this reaction. And so let's take step one and let's figure out the molecularity and the rate law. The molecularity is unimolecular, right? This reaction is only dependent on A. And because we know these are elementary steps, we can draw the rate law directly. And so one thing to emphasize here is under normal experimental conditions, if you don't know the steps in a process, you can't just draw the rate law. You have to figure that out from experimental things. If you do know the steps or figure that out in some way, you can know the molecularity. You can also draw the rate law directly. And it basically says rate is equal to K times concentration of A. And so step two, you need a B reacting with two C's. That's called termolecular. And so we're going back to Latin roots: unimolecular, bimolecular, termolecular, so on and so forth. The number of species involved dictates the molecularity of the reaction. And we can draw a rate law. And we know, because this is an elementary step, B has to react with two C's, and it gives you a rate law that looks like this. Next one's bimolecular, rate is equal to D times E. Bimolecular, rate is equal to F2. And so this is basically F times F. And so this tells you the molecularity and the rate law for individual steps, but it doesn't tell you the overall rate law. And so the overall rate law is going to be dictated by something else. You basically have to experimentally determine the overall rate law. And the key thing that allows us to do that is the rate law, the overall rate law is dictated by the slowest step of the reaction. And so what do we mean by that? What we're effectively describing is something called the rate limiting step or rate determining step. Basically says we have 10 steps in a process. One of them is going to be slower. Rarely will you have where all 10 steps are the same speed. Instead, there's going to be one step that has a higher activation barrier, and it's just going to be slower overall. And that slow step is what dictates everything. And so here's just a classical analogy using sand and like some kind of funnel system. You can see there's large openings here, and there's a narrow opening here. And so if you dump sand in the top, you can say this is reactant and this is product. The thing that dictates how fast this happens is this neck right here. And so you can think about that as step one in a three-step process. Step one is here, step two is here, step three is here. Step one is what dictates everything. You can't pour sand faster because it's limited by this right here. That's why it's the rate limiting step. If instead you have the narrow neck on the third step, these two are fast, this one's going to be slow. And so sand is going to go here, but you can't go any faster than this part right here. And so in this case, because the neck is narrow, both of these are going to take the same amount of time, but the rate limiting step here is step one. The rate limiting step here is the third one. And so you can think about this narrowness as an analogy to the activation barrier. The narrower it is, the higher the activation barrier, the slower that step is going to be. And so looking back at our reaction coordinate diagram, we have a similar bottleneck issue, right? So we have a step one, and then we have a step two. And you can look at both of these and you can say, well, the hill to get over that is pretty small. And so since this activation energy is small, this is going to be a fast process. However, this one here, you can see you have to get over a huge hill. And so it's going to take you time. And so we can relate activation energy to the rate of the reaction. The higher the activation energy, the smaller the rate constant, the slower the rate of the reaction. And because EA1 is so much bigger than EA2, this is going to be your slow step. And so that is your rate determining step for this reaction. It is the rate limiting. It is the smaller bottleneck. It basically says you can start here, it'll get over, you'll generate intermediates, and immediately it'll go here. There's no scenario where this is slower than doing this process here. And so because we know the step with the bigger hill is the rate limiting step, we know what dictates the overall rate. It's this step right here in this particular example. And so we have step one, which is slow, step two, that is fast. We can see that in that depiction right here. We can write a rate law for each one of those steps, right? And so if we want to do a rate law for step one, or there's the overall reaction, so NO, N2O2, N2O2 plus O2 giving 2NO2. That's an intermediate that gets canceled out. There's the overall reaction. We know this is bimolecular, two of those involved, two of those involved. We can also draw the rate law directly. Remember, the assumption here is that it's two steps, and these are the species involved. We're going to say rate is equal to K times NO to the 2. Rate is equal to K N2O2 times O2. And so we know that the overall rate law is dictated by the slow step, and we showed previously that the step one has the bigger hill. And so if that's the case, this becomes relatively straightforward. The overall rate law is simply rate is equal to K times NO to the 2. And so again, this shows why you can have a scenario where stoichiometry has to be experimentally determined, and also rate is equal to k no to the x, O2 to the y. When you do that fitting, and you figure out what the actual exponents are, O2 is 0, because O2 is only involved in the second step. It doesn't affect that first step at all. And so the rate is entirely limited by what happens here. That's the slow hill, that's the big hill we have to get over. The overall rate law is dictated by this right here. And so we can have very complex systems. Here's just an example. We have reactants over here, products over here. We have a 3-step process, 1, 2, 3, and we find out looking at this which one's the bigger hill, and the answer is step 2. And so in this case, step 2 is the slow step and the other 2 are fast. And so this gets complicated because we can't just use step 1 to draw the rate law. Instead, we know the overall rate law is dictated by the slowest step. Rate is equal to k times N2O2 times H2. And so that's step 2. That's your step 2 rate law. It's a bimolecular reaction. There's your rate law for step 2. But we have a rule in terms of drawing rate laws, and the answer is we can't write the rate law in terms of intermediates. Instead, we have to replace intermediates with reactants because we only write the rate law in terms of reactants. And so while this is true, this is what's rate limiting the process, we don't do that in terms of bookkeeping because N2O2 isn't something we have in a jar, right? We start here, we end here. N2O2 exists during this process, but we don't write our rate laws based on it. And so what we do instead is we do a couple of assumptions, which this turns out to be true. If this second step is slow, it means the first step is at equilibrium. It basically says it's going to go back and forth, back and forth, back and forth, and sometimes some are going to go this way. And so with that assumption, basically we can say there's a rate constant for forward, there's a rate constant for reverse, there's a rate law for forward, there's a rate law for reverse, and we can basically set these equal because at equilibrium they're going to be equal, which we'll get into more in chapter 13. But we basically can rearrange this and do an algebraic substitution where we can remove N2O2 because we know N2O2, the formation of that or the concentration of that, is basically going to be dictated by what happens in this first step. And so there's what we have. We can substitute that in that equation, and here's the overall rate law. And so, yeah, there's your overall rate law. And the thing we've translated here is we've substituted N2O2 for this equilibrium equation here. Now we've defined it in terms of the concentration of reactants, right? It's in terms of H2 and NO. NO to the 2, H2 to the 1. We've also combined a whole bunch of rate constants to give us an overall observed rate constant. And so a couple important points from this. You can't write a rate law in terms of intermediates, so you substitute in until you get reactants. Also, there's a rate constant for each individual step, but there's also a rate constant for the overall reaction, and this is typically called K observed. So again, this highlights the complexity of you can't just take the stoichiometry and write a rate law unless you know it's one step, then you can get away with it. But if it's a multi-step process, you have to know which one's the slow step. If it's the first step, the rate law is just the rate law for the first step. If it's the second or third step, you have to do algebra to substitute in until you can put it in terms of reactants rather than in terms of intermediates. All right, so that basically summarizes that again. K observed is the experimentally measured rate constant for the overall reaction. And so if you do temperature dependence and you figure out the activation energy and a rate constant, what you're actually measuring is this second step here, or a sum of first and second steps based on these rate constants here. Overall, the rate law has to only contain reactants. You can't have intermediates in there. And again, this is why it's so complex. You can't just write a rate law based on stoichiometry. You have to write it based on experimental data. All right, so if you're an experimentalist in this world of chemical kinetics, you figure out how fast something's going, you figure out the species involved. Ultimately, you want to propose a mechanism, because a mechanism is how you troubleshoot it and make it better. And so if you're a experimentalist, you're essentially going to monitor concentration and time. You're going to figure out a rate law for the reaction. And then from that rate law, you're going to kind of reverse engineer what is the mechanism of this process. And so you basically need to follow a few simple rules. Depending on the number of steps, elementary steps must add up to the overall balanced equation. You know where you started, you know where you ended, you have to do the math so it comes out where you start and where you end, which means your intermediates, if they're generated, they have to be canceled on the opposite side. The mechanism must correlate experimentally with established law. If your rate limiting step is the second step, then that better correlate with your overall rate law. Elementary steps must be physically and chemically reasonable. I mean, this is just, you can't say magic happens at step 2, right? You can't say the magic elf made A turn into B. You have to have something that chemically makes sense, bonds breaking, bonds making. And finally, the mechanism should be as simple as possible while still agreeing with experiment. This is kind of the Occam's razor of chemical kinetics, where why add extra steps if you don't need them? Nature likes to do the thermodynamically and, easiest pathway. Our assumption should be that our reaction mechanism is as simple as possible model. And so again, this is a very real thing, that if you're going to do reaction, if you're going to synthesize anything, you have to look at the data and say, what do I think is happening? I'm going to propose a reaction mechanism, and I'm going to draw a reaction coordinate diagram and say, here's what I think is happening. Does it agree with data? If it does, can I change it to make it better, faster, more efficient, so on and so forth. All right, there's our summary. We have our, reaction coordinate diagrams. We have transition states at the peak. We have intermediates between each individual step. We're effectively talking about what actually happens as the reaction progresses. And so we have reactants on one side, products on the other, a whole bunch of hills. At the peak of the hill is a transition state. In the valleys are the intermediate species. And then from that information, we can start talking about molecularity and rate laws, like how many steps are there, what's the rate law for individual steps, and also what's the rate law of the overall process. And the answer is the rate law for an overall reaction is going to be dictated by the slowest step. Which one is the tallest hill? Which one is the hardest to overcome? That is your bottleneck. That's what's going to slow down everything. And then we know that we can do some algebra and translate it in terms of reactants. And then ultimately, if you're going to do this as an experimentalist, you're going to propose this from scratch, basically. You're going to do the experiments, find out rate laws, find out concentration time relationships, and you're going to figure out, what's the molecularity, what's the overall rate law for the reaction, and what steps might be involved in this process. All right, so we'll close out. We've closed out reaction mechanism, what's happening during the process. Next video, we'll talk about catalysis, which is effectively trying to manipulate what happens during the course of the reaction, and that's what's going to dictate the speed of the reaction.